All right, welcome back, everybody. So we're here for lecture two from the series on the rational delta conjecture by Alessandro.
Okay, thank you. Okay, now today we're gonna go a bit more into the actual contents of the paper, but I guess today's lecture is gonna have like a large overlap with last year's lecture by Maria Gillespie because I need to introduce like the involution, the argument basically by Gillespie, Gorsky, and Sean listening here. So most of that argument is used like in the exact same way in our work. So I got mention it again. And so for those of you who listened last year's course, that's gonna be a nice refreshment, I guess. And for those of you who didn't, well, I mean, it's a very good argument, so I hope you like it. Okay. So today I'm going over pretty much what's section 4 in our paper. So we want to, okay, we have
Ah,
this.
you
Hmm?
want to share screen?
Oh, absolutely. I am not. Yeah. There we go. I thought I was already doing that. Okay. So as I said, I'm going over section 4 of our paper. So I mean, I'm going to give a combinatorial interpretation of this gadget here. So we know what this is. This is the generating series of rectangular dict paths of size m n plus mk. I guess I'm doing a really terrible example because they're gonna be quite tall. 8, 4. So in this case, we have m equals 4, which is the width, and the height is 8. I guess we can do n equals 4, k equals 1. Well, this is a terrible example. Let's do n equals 5. So at least we have n different from m, which is kind of the whole point of the thing. All right. And then again, we have some labeling. 7 again, something like this. So we recall that this object here is the generating series of labeled dict paths of size m n plus km q to the dim t to the area x to the pi. For today, I plan to pretty much ignore the div. We'll focus on the area and the monomials and try to respect all that and see what's going on in this sense. And then in the next lectures, we're gonna like actually go over the details of what the div is and how it changes with this process. But for now, let's just understand the combinatorial argument without it because it's a lot more simple. So first thing is, what is this gadget here doing? So one way to see the skewing operator is to look at this identity here. So let's say we have f and g, any two symmetric functions. I can think of, well, g perp f as g perp in some y set of variables applied to f, statistically evaluated in some x plus y alphabet. and then set y equal to 0. What does this mean? Basically, well, this identity is pretty much obvious once you understand what these objects are, what the scalar products are doing here. But on the combinatorial side, what we're saying is that, okay, we have a symmetric function f. We probabilistically evaluate it in a sum of alphabets, meaning we can use, say, two different sets of variables. And since f is symmetric, we can order them in any way we like. And then when we skew by this gy, we're sort of looking at the coefficients. Well, if this is some basis element, then we're looking at the coefficients of this expansion in the basis, like that's of which g is some element. And then when we set y equals 0, we're saying, okay, we sort of delete the labels that are prescribed by y, and then we're left with what we are left. Let's do some concrete examples, so maybe it's a bit more clear. If g is some homogeneous symmetric function, the homogeneous and the monomial symmetric functions are dual. So what this is saying, okay, we expand this thing in y in the we look at the monomial expansion in the y variables, thinking of like the x variables as coefficients. We look at the coefficient of m alpha, and then applying the skewing by h alpha is just saying, okay, we look at that one coefficient. So in our context, what's going on is if we apply some h alpha skewing operator to this thing, we're saying we look at some terms that have labels prescribed by alpha in some sense. So all of this to say, look, it's going to be a lot more clear when I do an example later, but the thing we want to do is to give an homogeneous expansion of this guy here, because skewing by homogeneous symmetric functions is relatively easy. We just have to look at the coefficient of the corresponding monomial. And so the first statement, which is, I think it's due to Gilles, Pygorsky, and Griffin, then Sean can correct me if it was already known, but I don't think it was. This thing here, the homogeneous expansion is given by, well, sort of, but it's equal to the sum of alpha allowable, and then I'm gonna say soon what this means, of -1 to the sine of alpha h alpha bar modulo hj, the ideal generated by the hj for j greater than m, where alpha bar is the composition such that alpha bar I is m minus alpha I. And the sine of alpha is the number of entries, the number of indices, such that alpha I is 0. So alpha, I guess I have to say what it is. Alpha is a weak composition of k times n minus 1, because the degree has to be what it is, of length k. Okay. So what do I mean by allowable? Well, allowable compositions are what are also known as Fubini rankings. So think of this. Say alpha n is allowable if it counts possible play. Well, I guess if it is possible placement. The content of and competitors in a tournament with ties allowed. Okay, this is all very messy, but now it's gonna be pretty clear. Suppose we have n people that enter a tournament. We number them from 1 to n. Let's do an actual example. I don't know, n equal 6. They compete and then they get some ranking and then they can tie. So for example, we're gonna have competitor number 2 arriving first, and then competitors 1, 3, and 6 tied for second place. And then competitor number 5 is now fifth because, well, these 3 people are like taking the second, third, and fourth spot. And then competitor number 4 ranks 6th. So this thing here is a Fubini ranking, I think. That's how it's called. And the content of this is the like how many people we have in each placement. So in this case, we have 1 person in first place, 3 people in second place, no one in third and fourth place, 1 person in fifth place, 1 person in sixth place. So this is allowable. So allowable compositions are compositions that describe like the possible placements of n people that compete in a tournament with ties allowed. I guess this is the easiest way to picture that in your mind. All good so far? Okay. Then to get to alpha bar, sorry, this is wrong here. Alpha is a composition of k here, so that alpha bar is a composition of k times n minus 1 because the degree has to match. And here with the length, we're also counting the 0 inside. I'm saying we have k people competing, and so they can only rank up to k. So I guess it's also easier and more consistent if I just call this k all over the place. Okay. Very well. Let's do a bunch of more examples of this, because then we need to write an involution on these objects. So we have that one example is this word here. Another example, we're gonna have, say, competitors 2 and 3 tied for first, competitor 1 ranking third, and then 4 and 6 ranking tied for fourth, then 5 that is sixth. You write another one, we can have 1, 1, 3 here, 3 here, and 5 and 6. It's also possible. Or an example with all, well, it's kind of easy, but they can all rank differently, and that's also fun. Why do we care about these things? Because on these things, there is a nice sign reversing involution that preserves tide inversions. What do I mean? So the sign, we said it's the number of places that are skipped. So it's k minus the number of different rankings you see. Well, minus 1 to that, like the parity of this thing. And our sign reversing involution, I'll put it down. Does as follows. So we let P be the largest entry in the world such that there is only one of it. And if, yeah, no. If Q is the largest entry less than P, then P is to the left of every Q. There might be no such entry, but if there is one, that's what we call P. And then we let R be the largest repeated entry in the world. Okay. Also, this might again not exist. So let's see in our examples what's going on. So in the first example, who is P? Well, we need to look at the entries of such that there is only one occurrence. So P is okay. Let's look at 6 because it's the largest such entry, and then we see that all the 5s are to the right of 6. So P is to the left of every 5, and so in this case, P is 6. In this second picture here, the entry, like the largest entry smaller than 6 is 4, but one of the 4s is to the left of the 6. So 6 is not a candidate for P. 4 is not either because there's more than one 4, but 3 satisfies the requirements because all the ones, which is the smallest entry, the largest entry smaller than 3, appear to the right of that 3. So in this case, we have P equals 3. What's happening here? Here we have our 6, but there is one 5 to its left, so it's no good. We have 5, but there is one 3 to its left, so it's also no good. And then 1 and 3 are both repeated, so they're also not possible. They're not candidates for P, so there is no P. And here, again, 6 is the largest entry, 5 it's to its right, and there's only the only 5 that appears. So again, P is 6. Yeah. How about R? Well, this is easier. Here we have R equals 3 because it's the largest and the only repeated entry. Sorry, equals 2. Apologies. Here we have R equals 4. Here how R equals 3, and here there is no repeated entry, so we don't have any R. So what do we do? There are 3 possible cases. Case 1 is P is greater than R, or R does not exist. In this case, we replace P point Q. So for example, this is happening in this case here, and in this case here. Yeah. So P is 6 in both cases, and in both cases, Q is the largest entries and P is 5. So they are mapped to, we just replace 6 with the 5. Okay. Case 2, I have to scroll a little bit, but then I'll go back up. P is less than R, or there is no P. In which case, we replace the first R with S minus 1, where S is the smallest entry in the word, larger than R, or it's K plus 1 if R is the maximum. So this is happening here and here. P is smaller than R, or there is no P. So we take the first occurrence of R, which is the largest repeated label. Here it's 4, here it's 3. We look at the first thing, like the smallest thing that's greater than R. So in this case, here's 6, here's 5. And we replace the first 4 with that thing minus 1. So in this case, we get 3, 1, 1, 5, 6, 4. And here we get 1, sorry, 4, 5, 6, 1, 3. Okay. The third case is very simple, as there are no P and no R. But then what's happening? Like we're saying there is no repeated label, and for each label, all the thing that's immediately smaller, it's to its left. It's to its right. No, it's to its left, yeah. And this can only happen if our word is exactly 1, 2, 3, 4, 6. Because as soon as you have an inversion, you have something that has the letter that is immediately smaller to its right, and that means you can that's your P. To have no P, we have to have this series of inequalities. To have no R, the letters have to be all distinct. So this is the only case. And in this case, we do nothing. Okay. So I think it's this map here is an involution. It is sign reversing. To see that sign reversing is very easy actually, because basically here we're replacing one letter, of which we have just one instance, with something that was already in the word. So we are changing the number of distinct entries. Remember, the sign is given by the number of like missing entries. Here we're taking something of which we have one of, and we replace it with something that we already had. So there's one more missing entry, and so the sign changes. Here we're taking something of which we have multiples, and we replace with something that that was missing, because we had S was the smallest thing larger than R. So if we put it in S minus 1, then S minus 1 is strictly smaller than s, so it was missing in the word. And we cannot have that. Oh, unless, okay, I guess there is one case, it's a bit odd, in which s is exactly r plus 1. I think this cannot happen. Maybe it's fine. If s is exactly r plus 1, then we're replacing that we're doing nothing, which is not okay. Give me a second, sorry. What's happening in that case? I think this cannot happen. Why can it not? I'll think about it later. Anyway, that should not happen. Oh yeah, no, sorry. Obviously it cannot happen because R is repeated, means we have at least, well, two of them, so the rank immediately after R is skipped. If we have two people tied for third, then there can be no one in fourth place. So the smallest entry larger than R cannot be R plus 1. Sorry. All right. And this thing is also an involution. Let's try to reverse it and see what happens. So we'll see why this is the case. So if we look at this word here, now R is 5, because it's the largest repeated label. And P, well, only one is non-repeated, so there is no P, so we fall again in this case. And what we do in this case is to take the first occurrence of the repeated label and replace it with like K in this case. Here we're in the case in which there is no, which R is already the maximal entry in the word. So we replace it with an occurrence of 6. So in this case, we're exactly going back. And the same is happening in all the others. And what's really going on is like here, the condition of this being to the left of all the things that are immediately smaller means that once you apply the function, this position is going to be the first occurrence of the largest repeated letter by construction. And so when you go back, you're replacing this with the largest thing that was not there before. So that's pretty much what's going on in this verse. And the other way around, let's see an example of case 2. We have replaced this 4 with 5. Now 5, we obtain it by replacing the leftmost 4. So by construction, all the 4s are to its right. And so this is the largest entry with this property, because if there was anything larger before, then that would have been the value of P before, which is not the case. So here 5 is the largest entry. 5, with such that the entry immediately smaller only occur in its right. And so here P is 5, and what we do is we replace it with R, which is exactly going back again, this direction here. So this map here, which I think they call psi, is a sign reversing involution with 1 to k as only a fixed point. And we have a slightly stronger statement, is that it also preserves tied inversions. What do I mean? I mean that if I is less than j and if this implies that AI is greater or equal than AJ if and only if, sorry, this was a phi AI is greater or equal than phi AJ. And why so? Well, again, when we are in case 2, we are replacing one letter, the leftmost occurrence of one repeated letter with the one with something that's bigger. So all the other inequalities stay the same, and the only thing we have to check is like between these 5. Why is this not? And the force to its right, but then this was greater or equal than this before, and this is greater or equal than this after. And the same happens in the other case. We're replacing something with something smaller, but we're replacing the something such that the letter immediately smaller only occurs on the right, and we're replacing it with exactly that value, so all the other inequalities are the same, and this was greater or equal than this, now this is greater or equal than this. So this preserves these pied inversions. And this is the key to the whole argument, because now we can write this thing okay, this changes the content, but what we are going to show later, we can take it for good for now. It's this. Let us consider the paths. Okay. Let's go back to this picture here. Now case 1, which is not fantastic. Maybe I should make something a little different. Only slightly. Okay. Let me add another here. So we have a less trivial thing. So now m is still 4. We can take n equals 2 and k equals 2. Okay. So what we do now is also not fantastic as an example. Maybe one m will be a little smaller. Sorry, let me change it again. Say n equals 3. N equals 4. K equals 2. Search. Okay. Something like this. Maybe should this a little. Okay. Good. All right. So now we want to skew by this thing here, and we can write this thing as a sum of like complements of allowable compositions. So let's take some, well, alpha is a composition of 2 and is allowable. There are not many with this property. So say alpha is 1, 1. Then alpha bar would be m minus 1, m minus 1. It's 2, 2. And now recall that we can think of this thing as like a sum of 2 alphabets. What do I mean? I can label this gadget here, instead of labeling it with entries like from 1 to whatever, I can like add another alphabet after it with this condition. So they're not ordering is the usual, but then the barred numbers are larger than like the non-barred numbers. And in some sense, these represent our x's, these represent our y's. And so I can look at the things such that the coefficient of the y is like a complement of an allowable composition. So for example, I can have a labeling that looks like, say, 1, 3, say another 3. I can put here maybe a 7, 10 or something, then another 1. And then I can have 1 bar here, 2 bar here, 2 bar here. Right. There's a valid labeling in this alphabet here. And these paths, the paths such that like the Y labels form like the complement on allowable composition are the ones that are like that will appear when we skew by this thing. Because when we skew by this thing, again, we can see this as like looking at the objects labeled in two alphabets and then deleting the y's and then setting y equals 0, which means we have to be able to delete the y's that appear. So if I'm skewing by h alpha bar, I need to have at least alpha bar 1 bar 1s, alpha 2 bar 2s, and so on, because otherwise I could just get 0. I can't, like, the coefficient is not gonna be there. And then those have to be exactly the only like barred numbers appearing, because if not, when I set y equals to 0, that term also disappears. So when I want to look at this object here, I can restrict myself and just look at paths with this property here. So such that they're labeled in this alphabet here, and the barred labels for like the content given by the barred labels is the complement of some allowable composition. All good so far. I guess this can be a bit confusing if we're not familiar with pladism of this kind of arguments. Okay. Sorry. So when I look at one of these guys here, then I want to obtain one of the guys I had in the previous talk. Let's remember what we can do. We'll stick with the ENS representation because this makes bijection a little easier. So our objects are paths. Well, they can go down like this. So they can go east, north, or south. They go south exactly k times. And such that this never happens. So you never have a south-north sequence. Always, if you go south, then you have to go either south again or east. And then this one here doesn't even stay above the main diagonal, but this is actually a requirement that we don't need. So if we start from something that stays above the main diagonal here, we will end up with something that's above the main diagonal here, but we can completely disregard this restriction. And what happens, well, at least conjecturally, is that here, instead of EMN, we can plug in PMN. This is true if M and N are coprime, conjectural otherwise. So we also have a generating function for the same set of objects, except you can like disregard the restriction of being above the main diagonal. You can also go
Well,
below it.
Alessandro,
And
what
yeah,
is PMN?
Um, okay, that's a good question. So the way I think of this is EMN, let's say the GCD of these two is D. I think of this as some operator in the elliptical algebra applied to ED. Again, I can go into details, but and so with this notation here, PMN is the same thing, but you starts from PD. I
Okay,
guess
thanks.
I have to also have a correcting factor here, MQ over DQ. So if D is 1, PD and ED are both E1, so they're equal, and so we can use a combinatorial argument to like show that there are exactly Q analog of M times object, like for each path above them in diagonal, we have exactly M paths that go also below them in diagonal, and the dim changes in a way that's prescribed by the Q analog of M. So one of them is the same, one of them is +1, +2, and so on. If they're not co-prime, then these are actually different symmetric functions, and so it's a bit more complicated, and so we don't have a proof of this statement. So we have exactly the same formula. We have a thing, we have an area with the same monomial, except our paths here are not restricted to stay above them in the diagonal. And all we did still works for these paths. Like being above them in the diagonal is not really doing anything. We have the exact same restrictions, and if we start from something above, we end up with something above. If not, we don't. But well, this also, if we like, this also gives a decorated analog, well, a full version of the square analog, like a rectangular analog of the square conjecture. So the square conjecture is pretty much well, it's an analog of the shuffle theorem. Well, now it's a square theorem, I guess. um, that for paths that don't necessarily stay above them in diagonal. And so we have an analogous statement for this rectangular version, and via this argument, we also get the same for um, well, decorated paths that are on a rectangle and can go below them in diagonal. This was a bit more convoluted than I wanted, but anyway. What do we do here? We start from something like this. And then the combinatorial argument is very, very easy. We keep everything, the columns as they are. But then after each column, we go down by 2 steps, by k steps, where k is 2. So I go south, south, and then again, and then again. And then let me draw the labels on the left side because there is no space on the right. Okay. And then we get rid of the red labels, possibly with the corresponding subset. So what we get is this thing here. And of course, this is not bijective because we're losing the information given by the red labels. Well, I guess I have to label this thing here as well. But we can recover it by writing down the complement. So here we like the words is 1, 2, but like the length is up to 2. So there's nothing to do. There's no steps, there's no complement, there's nothing. Here we deleted the 2, so we kind of want to label this thing with 1. And here we deleted a 1 from the column, so we want to label this red step with a 2. If we add these labels here, then we can just reverse the construction. Like, because in each column, what we do is just we add 2 north steps labeled, well, as many north steps as needed, like labeling with the complement of what we already had. So to go back, here we add 2 steps labeled 1, 2. Here we have a step labeled 1 that dies, and we add 1 step labeled 2. And here again, we have 1 step labeled 2, so we add it back, something labeled 1. And this is pretty clearly bijective, I would say. And another property that this preserves is that the vertical distances between the endpoints of, well, all steps, I would say, and the main diagonal, they stay the same. So this distance here is the same as this distance here. Well, it's obvious because, well, it's 1, it's in the same diagonal. But for example, this distance here, it's the same as this distance here, because we're like moving down both the main diagonal and the height here by the same quantity, which is like an appropriate multiple of k. So they stay the same place. All of the stuff in this column is going down by 2. All the stuff in this column is going down by 4. All the stuff in this column is going down by 6, and so on. So this map preserves the vertical distances between the endpoints of steps and the main diagonal. In particular, if here the path is all above the main diagonal, it will also be above the main diagonal here, because all the steps end above the main diagonal. Well, the distance is positive, so it's the same. And this is going to be extremely important when we want to compare the div of this path here and this path here. Because if you remember what I said last time, the div is composed of a bunch of different summands. One of the summands is the number of attack relations between the labels, the temporary div. And that's going to be exactly the same, because the attack relations here are going to be exactly the attack relations here. Remember, we had an attack relation when AI was lexicographically less than AJJ, less than AI plus 1I. Now, if we use this ENS representation, then the diagonals are straight. So looking at the horizontal distance, which is this AI, or looking at the vertical distance is the same. Well, of course, the distances are not the same, but we have like this inequality holds if and only if, let me call VI the vertical distance. VII less or equal than VJJ less or equal. Now I'm going to write this wrong. This Is this m over n or n over m? I'm guessing m over n over n, obviously. I. Well, I mean, if the horizontal distance goes up by 1, the vertical distance goes up by the slope. So this holds if and only if this holds. Like they are scaled the same way, the distances, because the diagonal is straight. So that's what makes this representation especially useful. It's very easy to compare the distances, horizontal and vertical, it doesn't matter. If we use the previous interpretation with the broken diagonal, we can still do this and still look at the vertical distances and everything works fine. But then we don't have this the same only if. Like comparing the horizontal distance and comparing the vertical distances is like a lot more difficult. We have a lot of work to do here. It's a lot easier because the inequalities are just preserved. Like this, they're similar triangles, right? Like if this is greater than this, then also this is greater than this. These two triangles are similar. Okay. Well, I said a lot of things for today. The one last thing it's worth mentioning is that if we believe, I did not prove it yet, it's gonna happen in the next lectures, but if we believe that, hold on. Okay, sorry, let me go back. We go back to this picture. And by construction, the labels of this south steps here have allowable content because they are the complement of something whose complement was allowable, and so that's allowable by definition. And we can get a reading word by reading these labels from the farthest to the closest to the diagonal. So in this case, it's very easy. We get just 1, 2. Can have more complicated examples in which stuff happens. And then if we apply this phi map here, well, this map to to this word and change these labels accordingly, we get another path with the exact same div, but these two paths appear with different signs in the expansion of the skewed, in the expansion of, right, this expression. Because I'm skewing with two things that have opposite signs. In one case, I get one of the two, in one other case, I get the other of the two. And so when I write the corresponding combinatorial sum, the paths with, say, not complement, corresponding reading words cancel out. And so we can just restrict and just look paths in which these south steps are labeled from 1 to k, from the farthest to the closest to the diagonal. But that's exactly the same as like not labeling them at all. Like if I have just one possible way of labeling the south steps, I might as well not do it. So what I'm saying is that in the image of these things, I get like a sum of these things with some signs, and they cancel pairwise, except those whose reading, like south steps reading word is exactly 1, 2, blah, blah, up to k. And at that point, they're just paths with like south steps that are unlabeled, which is the set we wanted to obtain in the end. Okay, I don't think I can say much else for today. So I'm done. Again, if there are any questions,
Let's thank Alessandro. Very good. Uh, so anyone have any questions?
I have one. So for your more general conjecture on the P, like
Mhm.
did you have data on like how do you decide on your the area and the div? Is it the same or like you have to choose a little bit? Like what does
So,
that mean by
okay. So this conjecture here is actually from a previous work with the same authors and also with Anna van den Wingert. As I mentioned last time, like when I moved to Montreal, I started looking into these things, and we had these theta operators handy. So, well, this is kind of a natural extension. Like if you think of what's happening in the square case, you do nabla n, you get square, you get Vic paths. You do nabla pn, you get square paths. So replacing this E with P is kind of natural guess, and hoping to
Yep.
get the right thing. You do need this correcting factor pretty much for the reason I mentioned, because if M and N are coprime, then E1 is the same as P1, you get the same symmetric function. That doesn't make a lot of sense because you obviously have more paths that, like, if you ignore the restriction of thing above the diagonal. And yeah, the dim is pretty similar. There are a few little differences. Like what's happening in the square case is, let's say in the square case, and then you go below them in diagonal, you have to add one for each step that's below them in diagonal. Here it's a little bit different. I don't remember exactly, but you have to, they have to be at least one unit below them in diagonal, I think.
Okay.
No, sorry. Oh, no, not like that. I don't remember. Whatever. And then the correction, like you have a correction that depends on the shape above the path. And that's the same. Like, okay, your path can be below them in diagonal. You have a bigger shape here, so you have more like pairs of them. Like maybe I can recover the picture from the previous lecture. It's still stuff like this. You have more of them, but it's fine. And then for the decorated case, in the previous work, we did not have a dim. We did not have it even for the like regular above the main diagonal case. So yeah, this stuff, not this, but this stuff was all of it was Q equals 1. While in this context here, well, we already had the conjecture for just P because that's previous work. And then when you apply this argument to paths that go below them in diagonal, this sort of tells you what the dim should be here. I didn't do it today because I didn't mention the dim pretty much at all. But if you want the dim on this thing to be the same as the dim on this thing, then this is telling you what the dim here is. And then all you have to do is to find a decent communal interpretation, which is what we did in later sections. And that's what I'm going to explain in the next lectures. I don't know if that answers the question.
Thank you.
So I have kind of a big picture question. Maybe you
Mhm.
answered this in lecture one, but so you have this rise version for
Mhm.
rational of the delta.
Mhm.
But what about the valley? Is there a valley version for the a conjectural valley version?
I tried and I couldn't find anything because when you add back the valleys, it does get like messier.
I see.
It's like I really tried because I really
Yeah,
wanted
I'm
to
sure.
answer the question, but the I don't remember exactly what we had, but I vaguely remember it was something like that sort of worked in some very small cases, which is not fantastic. I know.
Mhm.
Um, I think. Sorry, give me a second here. Mm, No. I think that one problem is that, like in the previous lecture, I mentioned that when you take the scalar product with the n, you have a very natural symmetry between these things, like the things with decorated rises and decorated falls. And so
Right.
these things are sort of counted by this theta, aka mn, and these are counted by this symmetric function here. But this argument fails for volleys because the contractibility is an extra requirement that sort of like breaks the labelings and doesn't make it very nice. The
I
numbers
see.
are just not the same. So no, I guess I mean, I tried, but I couldn't find anything
Yeah.
nice.
So even with if you go way down to the end of your lecture here, even with these transformed things that have the nice south steps, um,
Mm-hmm.
this is not enough to get a valley version. Like there's no obvious thing. Okay.
I didn't really think much about this because the map we had, we really started with the broken diagonal things, and then we realized that this was a more convenient way to draw them. But I don't think we tried to get back a valley version from these objects. So maybe, yeah, maybe.
Okay. All right. Any other questions? Very good. Well, thank Alessandro again,
Thank you.
and we'll look forward to next week.
Great.
Hi, everyone.
Bye.